Hello everyone, I am currently traveling, but I wanted to take a moment to personally remind you that this coming Tuesday, April 29th, our next Quantum Online Industry Meeting will take place. The meeting will start at 10 a.m. Eastern, 7 a.m. Silicon Valley, and 4 p.m. in Central Europe. This online gathering will focus on both opportunities and challenges in developing the quantum internet. Number 1. Maintaining coherence across long distances. Number 2. Implementing error correction. And number 3. Integrating both quantum and classical networks. We have an outstanding lineup of speakers. Noel Goddard, the CEO of Qunnect, will be joined on the virtual stage by Matheus Sena from Deutsche Telekom to discuss entanglement distribution and telecom integration. Darras, the CEO of Welinq, will join them to share breakthroughs in commercial quantum memories. Afterwards, Manish Singh, the CEO of memQ, will be presenting advancements in quantum networking architectures. Janson of Nokia and Vanesa Diaz from LuxQuanta will highlight their collaboration on continuous variable quantum key distribution. And afterwards, Gilks, the head of quantum strategy at British Telekom, will outline BT's work in quantum communications for live networks. Last but not least, Daniele Sartorato of 𝐍𝐕𝐀 and Constantino Agnesi of ThinkQuantum will be sharing real-world quantum key distribution field trials. And this is not a webinar. Remember, this is an online gathering of experts looking for collaboration. We are all in the room, so let's get started. And we are all here after months of work on bringing new developments in quantum internet. We are all here, all of us together, lots of people in the Zoom room with one purpose. Over the next 90 minutes, we need to make sure that all of you find potential partners, suppliers, and customers in the room. And I quite like to start this meeting by saying something. It's been 3 and something years since we started this industrial push at Optica. We have seen many things happening, but especially in quantum, I would like to acknowledge the huge work of Qunnect and Welinq on the quantum memories. Because of you, we can have meetings like this. Because of you, we can have British Telecom and Deutsche Telekom believing that the quantum internet is real. So thank you very much on behalf of the quantum world for the great job that both of your companies are doing, Qunnect and Welinq. This meeting is spectacular, and it's spectacular because of the huge work of the Optica engagement team. As you all know, the meeting is the result of hard work scouting the best technologies for members, and it wouldn't be possible because if it wasn't because we have a sponsor, because none of you are paying for this hard work, but ThinkQuantum is. Thank you very much, ThinkQuantum, the QKD company that is pushing for us to keep trying to be the best of both worlds. And later on, ThinkQuantum is going to showcase one of the huge developments with an end user. So stay tuned. Before that, I would like to say this is, of course, the result of collaboration. We want to find collaboration between the companies here in Black Square and everyone else. So if what you wanted to do in the next 90 minutes is to listen and relax, change your mind, because that's not going to happen. Everyone in the room is supposed to speak their mind and see how they can collaborate with the success of the companies mentioned here: Qunnect, Deutsche Telekom, Welinq, memQ, Quant, Optical, Nokia, LuxQuanta, British Telecom, 𝐍𝐕𝐀, and ThinkQuantum. Thank you for your great support as Optica corporate members. Today's quantum internet, but in 2 weeks, in 1 week, anybody who is involved in gas sensing and liquid sensing, where you're making narrow linewidth lasers, spectroscopy, detectors, you have to come here. We have huge end users prepared to share their needs in the field of the field of gas and liquid sensing. But today is all about quantum. And what we want to do is to make sure that members keep being successful. So remember, because you're a corporate member, you have access to these networking activities, market reports, fantastic events, discounts, promotion, and engagement opportunities. And always, we have the largest database of market reports for our members. Go to optica.org/market reports, and you can download all of them there. But that's all. Let's talk today about quantum internet. This meeting is live streaming YouTube, so let me say hello to the YouTubers of the world. Hello, YouTubers of the world. You are not in the Zoom room, but if you have any questions, please write them in the chat, and I will read them in the meeting room. And that's, of course, also valid for the people here with me in Zoom. All of you, if you have questions, comments, suggestions, write them in the chat and you will speak your mind and you will make sure that your voice is heard. John Pugh, Dr. Pugh, Director of Quantum and Peak Technologies at Optica, congratulations on bringing together what in my opinion is the best possible agenda on quantum internet with end users and enablers. What makes you happy about the next 90 minutes?
What makes me happy is just that, I think, is we've got a great room of system integrators and technology enablers and people to ask them questions. It's great. So thank you. So yeah, good morning, afternoon, evening, wherever you are in the world. So we live in hugely exciting times considering the opportunities that quantum technologies afford. And that's, of course, why we're here today. So quantum technologies at an inflection point where we're seeing a significant shift from laboratory proofs and early stage commercial to actual infrastructure deployment. And this became very apparent recently at OFC in San Francisco. So, and aside from all the technological excitement, global industry and governments are evidently taking note that quantum technologies are indeed potent enough to revolutionize the entire industries. So that will inevitably reshape the geopolitical landscape. So we follow up the January online industry meeting on quantum communication with this meeting addressing specifically discussions of great progress and highlighting opportunity, but also addressing, as Jose introduced, the challenges in developing the quantum internet. So as Jose said, today is not a webinar. We'll have an interactive conversation engaging with the industry leaders here to understand how these innovations can drive the future of global communication networks and the realization of scalable quantum computing. So I'd like to thank in advance all of our speakers for joining this meeting today and being prepared to answer all your questions. So for today's first joint keynote, we're joined by two leaders shaping its future from both the innovation and infrastructure sides. Noel Goddard, CEO of Qunnect, brings a deep scientific and entrepreneurial perspective. Under her leadership, Qunnect is developing the core technologies for entanglement distribution over metropolitan scale networks, building quantum repeaters, memories, and sources that are actively being deployed in real-world environments. And Matheus Ribeiro Sena, representing Deutsche Telekom's Innovation Hub, plays a key role in advancing quantum communication strategies within one of Europe's largest telecom providers. His work focuses on integrating quantum technologies into scalable network infrastructure, ensuring secure and future-ready connectivity. Together, Noel and Matheus will explore how the quantum internet is evolving from theoretical promise to practical reality. From cutting-edge hardware to telecom-grade deployment, they'll share recent breakthroughs where together they've surpassed previous records for sustained high-fidelity transmission of entangled photons over commercial fiber network. Noel and Matheus, from the UK to USA and Germany, respectively, the floor and the attention of everyone is yours.
Thanks so much, John. It's very exciting to be here, and thank you to Optica for hosting this event. I think it really shows how far the industry has come to have this many speakers that are crossing between, again, having commercialized hardware from the laboratory to the market, and now actually deploying with customers worldwide. So it's an exciting day for all of us to be here. So as John said, Qunnect is a hardware company. We basically have spent the last few years developing a product suite which transforms existing telecom fiber into quantum networks. And in order to do that, we've been really focused on what sounds like a very simple but extremely important core problem. And that's the idea of how do you maintain high fidelity of quantum information as you distribute it across a network. If you can do that, then you can unlock applications. And we're here today to talk about the quantum internet. When I think of the quantum internet, I think of quantum channels connecting quantum devices. That means you can do things like secure communications, which some of our colleagues will speak about today. But you can also do other things like connecting quantum sensors for quantum sensor arrays. You connect quantum computers for distributed quantum computing. All of this is important, and it's going to unlock a very exciting future. What we're in particular focused on at Qunnect are two major sort of verticals. One is, how does entanglement enhance and provide enhanced security? In order to do that, Qunnect has been developing technologies for eavesdropper detection, position verification, and most recently, though it's not listed here, we're also concerned about electrical grid security. In this case, fiber channels carry both digital information and quantum information, but the quantum information enhances the security of the existing digital internet. The other thing which Qunnect has been spending a lot of time focused on from our very core mission, which was mentioned in the introduction, is this idea of how would you actually build an infrastructure where you could enable a quantum data center, or you could enable quantum repeating over long distances. That all has to do with integrating quantum memories into the existing quantum networking product suites. And when we can do that, we gain both the ability to route information within a data center, and then also the ability to do long distance quantum networking. So over the past 4 years, we're rather proud of the fact that we've brought a large number of products to market. And in fact, the system of those products was just nominated as a finalist for the Prism Awards in 2025. The product suite itself has some sort of very core pieces. One is that we have a number of instruments which, at their core, generate entangled photon pairs. We do this a little differently than the other commercial products on the market because everything that we do is based on rubidium vapor. There are some advantages to that, in particular for the types of networking protocols that we're pushing towards at Qunnect. One of the great advantages is that rubidium atoms themselves produce photons which are very identical in terms of their spectral output. When you have that, you can actually start to perform some of the more sophisticated protocols of teleportation and entanglement swapping, which again have low success rates unless you have the ability to generate identical photons. The other thing which rubidium vapor provides for us, which is rather unique, is the ability to have a local reference of very high quality so that every node in the network is actually locked onto something with extreme precision because you're actually locking to the atoms themselves. But that's not enough, because whenever you start to broadcast these photons through standard fiber, our photons are polarization qubits, so therefore they start to rotate as they go through standard telecom. You need to be able to correct for that. So Qunnect developed this other instrument called the QAPC that actually actively tests the fiber channel that you're sending information through and then compensates for any real-time aberrations which are caused by environmental changes such as wind, rush hour, temperature. And then finally, of course, we have instruments to validate on the other side so that you can use this in order to build protocols, and software which seamlessly integrates our instruments with some third-party timing electronics and also with some third-party detectors. Since the beginning, we've been really determined to push all of this into a telecom-compatible standard form factor, which you see there. And we're very proud of the fact that the first racks themselves were sold last summer. We have a number of orders for this coming year. And the company has actually done $2 million in real-world business. So this is hardware going to customers. Very exciting. So in order to show that this stuff works well, we, in the middle of last year, actually published a publication on being able to build a network in New York City. This, again, was started with existing telecom fiber. All that the company actually did for us was to fuse it together so that we would have the paths that you see on the map here. Our first experiments that were demonstrated in the literature were on the purple loop that you see to the right, which is 34 kilometers running through Brooklyn and Queens. We, at the time, held the record for being able to keep our network 24/7 on for more than 15 days straight. We broadcast as high as 500,000 pairs per second that we were able to actually preserve with extremely high quality, 99% network uptime. And now we have other partners, which you see the other racks in Manhattan there, some at NYU and some at a data center called QTD. And as we come through 2025, we're planning these multi-node demonstrations of more sophisticated protocols. So stay tuned. And the other thing which is on our horizon is that integration of the quantum memories that I mentioned before. So in 2021, Qunnect was the first company in the world to commercialize a quantum memory. Our memories are a little different than the other ones which are coming to market right now because they are room temperature quantum memories in the truest sense of the word. There's no external cooling and or vacuum required to operate them. Because they're room temperature, of course, they have some performance limitations, the same way as every quantum memory has some performance limitations at this point. But we think it's a very powerful message that you start off with something that you know can actually fit in the existing infrastructure, and you push it to its limits so that you can actually start to think about how it integrates into real-world protocols. So what we've done is we've actually started projects where we're starting to interface our source and our memory. And in fact, we have a publication that was just posted on arXiv of our most recent results doing so. Our first generation memory, which we're rather proud of when we launched it, right, is spec'd at about 150 microseconds of storage time, but it had a very narrow acceptance line width, which meant that it's sort of picky about the photons that it takes in. We knew that in order to be able to both optimize the interfacial losses with the entanglement source and to make it better for eventually what's going to be necessary for networking, we needed a new generation. We call that one our broadband memory, and that's the one that you'll see in the publication, which is highlighted there. We're very proud of the fact it's the first demonstration of a Telekom photon entangled with a room temperature memory, and we're able to get fidelities higher than 90%. So this is a very exciting time. I think one of the things we never think about is that all of these details of how to do things like optimization of interfacing sources and memories, optimization of fidelity of channels in order to continuously do broadcasting of distributed entanglement. All of those things are how we get to commercial being a quantum being a real world commercial entity. And we're very excited for what lies ahead. So our team is just now 22 people. We work in the Brooklyn Navy Yard. The two buildings that you see there on the right are at either ends of the Brooklyn Navy Yard campus. And we also recently opened an office in the Netherlands. So we're really very excited to work with US and EU partners. So please give us a ring if some of this is exciting to you. And we're very proud of the fact that we sell hardware, not hype. Thank you.
Great, thank you, Noel. Should we move straight through to Matheus, and then we can take questions at the end of the joint presentation? Thank you.
Yeah, I hope you can see my presentation now, right?
It's just coming through. Yep, great. Thanks, Matheus.
Yeah, perfect. Yeah, so first of all, thank you for the invitation, John, Jose, and Noel. So it's a great pleasure to talk about the quantum internet in this very warm afternoon here in Berlin. And I think my contribution here is maybe to highlight the importance of these industrial collaborations for the realization of the quantum internet. So we certainly need big players like telco operators working together with key technology developers in order to make this vision become a reality, right? But before I talk about this, let me quickly introduce the T-Labs and show what we are doing concerning quantum networks. So we are the Research and Development Department of Deutsche Telekom, and our role is to act as a bridge between this innovation ecosystem formed by small, medium, and large startups, research organizations, universities, and these three main units of Deutsche Telekom, which are business, technology, and the security unit. So at T-Labs, we have a quantum networks tribe. That's a team of about 8 people with diverse backgrounds, including quantum physicists, electrical engineers, computer scientists. And each member plays a crucial role in the process of transferring the knowledge as we work to bring this quantum technology know-how into the telco world, into the telco business, right? So that being said, we have a research topic portfolio that englobes quantum key distribution, post-quantum cryptography, the use of entanglement as a resource for quantum repeaters, quantum sensing, quantum-based time synchronization, and etc. But at the end of the day, we have a big mission, which is to prepare our networks for a quantum connected world. And I'm not only talking about QKD, that's one application, but we foresee multiple business opportunities with the advent of the quantum internet, as Noel has already mentioned, yeah. And I think our biggest asset to help us answer these questions is our R&D fiber network. So we have more than 3,000 kilometers of optical fiber cables disposed in this ring network around Germany and connecting main cities like Berlin, Munich, and Frankfurt. And that's only used for R&D purposes. And within this network, we have the Welinq quantum testbed, which has more than 2,000 kilometers of dark fibers, which are constantly being used in our quantum-based field trials. And at the center of the Welinq testbed is our quantum lab that was inaugurated in August of 2023, although the group already existed, yeah, but the lab is quite new. So the lab is the door to this network, so to say, and it's where we run our experiments together with startups, universities. So we invite them to come to us to test their solutions in a telco environment. So this is just a sneak peek into our lab. It has 80 square meters. It's in Berlin with approximately 10 racks in which we have QKD, entanglement distribution, PQC setups running and being tested 24/7. It looks a little different than a regular quantum optics lab where you find in a university, because we don't have optical tables there. So that's one of the requirements for our partners, that they bring solutions that must be rack mountable and comply with basic data center criteria. And I wanted to show this because not only because it's an invitation for companies that are watching us right now and want to collaborate with us, but if you are also in Berlin and want to have a look at the lab, just contact me and it will be a pleasure to give you a tour. So to finalize this presentation, I'd like to give you an example of a successful collaboration between us and Qunnect that shows how this telco startup collaboration framework works out. Yeah, and I have to say that Optica had a very important impact on this, because actually I got to know Qunnect after seeing this post from you, Jose, on LinkedIn. Yeah, so it was back in 2023. You were visiting the office of Qunnect in Brooklyn and showing what Mehdi was doing at the time they were doing this entanglement distribution in New York. And I thought, these guys are doing something similar to what we are doing here in Berlin. Yeah, at the time we were already doing some entanglement distribution here, but we wanted to increase the performance. We wanted to work with the state of the art in terms of devices. Then I contacted Mehdi. We had a first meeting at ECOC 2023 in Glasgow. And then we saw this very synergetic cooperation between us. So we could offer our infrastructure. We can offer our telecom know-how, so the guys from Qunnect can understand what are the criteria for building the quantum internet, for building quantum hardware for the telecom environment. And in return, we want to use their hardware. We want to test them in our network. We want to gain this quantum know-how in order to disseminate within the company. Yeah, in 2024, beginning of 2025, we've been actively working in exploring many possibilities with the Qunnect devices. So one of the results we showed at OFC beginning of this month, which was a record-breaking result where we transmitted the photons, the entangled photons, for 17 days without interruption, with fidelity higher than 99% and downtime of 1%. Yeah, using the sources from Qunnect and the APC, the system that controls the polarization. Yeah, and we've been extending the setup to transmit the photons over 82 kilometers with co-propagating classical light, doing switching between different nodes within Berlin. Yeah, so we've been trying to explore this technology to see what kind of topologies are the best, what kind of the parameters that must be optimized. And yeah, so we've been exploring the technology a lot over the past months. Yeah, and that's it. That's a very good example of collaboration in this framework, big telco with a startup. And I think it has worked quite well. And I think this is a very important step and a very important attitude from big players in order to somehow drive the technology forward. Yeah.
Great. Thanks, Matheus and Noel. I think you can see by Jose's reaction, that's music to his ears, and ours, of course. So just going to a few questions. If there's questions, please write them in the chat. We can unmute you and you can ask the questions yourselves. But given this sort of focus on quantum networking infrastructure, where do you see the greatest need or opportunity for collaboration with external partners? Is it technology development? Is it commercialization? Or is it network development, network deployment even?
Is the question for me or for Noel?
For both of you, if you're...
You can go first, Matheus.
Yeah, I think as I mentioned, there is this knowledge transfer right now. And I think there's a great opportunity for these collaborations in order to somehow so that we can gain that knowledge and disseminate within the company right now. Because right now we don't have a quantum internet, but we're going to have that in I don't know how many years, but we're going to have that someday. Yeah, and the company and the workforce, the people that work there, yeah, must be prepared for this new concepts: entanglement, superposition, yeah, entanglement swapping, teleportation. This is something new. That's not something that you are used to if you have a telco background. And we are working on this knowledge transfer, so to say, and that's where I see the biggest opportunity at the moment within this framework.
Great.
So I echo that. I think that the important thing for quantum startups is that more often than not, their products are not at the advanced level. It's one thing to take a product and take it from a laboratory to commercialization. It's a second big leap to take it from a commercialized product that is good for researchers and make it into something which is ready for network operators to use. So that sort of industry hardening step is something which is another large development step for everybody in our community. It's best done when we have collaborators who give us a wish list of what they would want to see in a product. And I think one of the things that quantum startups have struggled with is there hasn't been a lot of market customer information and wish list sharing, because more often than not, particularly in this case, network operators don't know the potential of the products. So it's a give and take conversation now of these are the first products on the market, these are the specs we can do today. If we could develop something that looked more like what you want, that would work best in your system, what would that look like? And that feedback is critical to startups everywhere for making better products.
Great. I think that's a great call for that. So a question to you, Noel, is you showed the Gotham rack format. And where do you see the sort of future? Where do you see this going? In terms of like miniaturization of systems, what does the next generation look like?
So definitely everything that we do is in 2U rack boxes. And I think that was just because we had to decide that there was some footprint that we would all aim towards at the beginning. Again, it's going from a table to a box, and you just have to pick the box size, right? You have so many challenges even at 2U when it comes to learning how to stabilize things. What's ironic is that as you start to miniaturize, you get better on stability. But some of the things with quantum have these bespoke elements, like in our case, the vapor cell, which don't lend themselves to miniaturization as well, in their entire research groups devoted to worrying about these things. We certainly would love to take the next step. So I think, if you were to open up one of our boxes today, you'll see a combination of adjustable optics and fixed optics, depending on the maturity of the pieces. When everything finally becomes fixed optics, then it will eventually start to be miniaturized. And then the magic happens that right now, I think every quantum company here would be hard pressed to tell you that the margins are great on quantum hardware. They will not be great until it gets to miniaturization, and you can actually use contract manufacturers in a way that gets the prices down so that you can have real margins.
Great, thanks for that. Jose, are there any questions in the Zoom room?
There are a lot of people who I want them to say hello in a meeting like this one, because we are trying our best, not only to make cool videos, thank you so much, Deutsche Telekom, on this, but we also want to make sure that the end users drive our conversation. So there's a couple of people I want to say hello. Alberto Coming from Airbus. Thank you very much for joining the meeting today. Of course, you are always looking at the very safe quantum communication. Since the last time that we met, what kind of things have you seen that are making you really excited? Alberto, we can't hear you. Somewhere in the cloud. And I will take the time to say hello to all the Spanish people in Spain. You all have electricity, I heard, so congratulations on that. Alberto, can we hear you now? I think we can't, but we'll come back to you. I'll come back to you later on today. In the meantime, I also would like, when it comes to high energy physics, everybody loves the Large Hadron Collider. We love Switzerland. And we have here Annick Tippe from CERN. Annick, quantum communication engineer from CERN. Thank you very much for joining the meeting today. Could you tell us a bit what you're working on and what are your biggest headaches when it comes to quantum communication?
Hi, everyone. Thanks for asking, Jose. Nice to see you all. Yeah, so indeed at CERN, we're also busy with working on quantum networks. And we aim to implement a technology that has actually been developed at CERN in our quantum network, which is the White Rabbit technology, which was originally designed for the accelerator. So White Rabbit is a precision time protocol to very accurately distribute both time and frequency over a network. And that's exactly what we will be using in our quantum network. So for us, the challenge is to improve this technology. So it's based on the challenge is synchronization.
Anik is always looking for partnership, for opportunities. And after that statement, be prepared to have lots of introductions by email after the meeting. You know how this works. Back to you, John.
Jose, yeah. So at this point, I'd like to sort of bring into the conversation two pioneering startups who are at the forefront of quantum networking. So they each address critical challenges in scaling quantum technologies through innovative approaches to quantum memories and photonic interconnects. So firstly, we're joined by Tom Darras, co-founder and CEO of Welinq, a company at the cutting edge of quantum communication technologies. So Welinq's new record-breaking commercial quantum memory is a fully integrated system allowing for plug-and-play deployment in quantum data centers and quantum communication networks. Tom, the floor and attention of everyone is yours to tell us more about Welinq and QDrive.
Thank you very much for the kind introduction. Hello everyone. It's really a pleasure for me to be here today. My name is Tom Darras. I'm the CEO and co-founder of Welinq. We're a French quantum networking company based in Paris, in France. We have, as of today, 30 full-time employees in our company. Well, as you know, quantum technologies are currently transforming many industry sectors. But for this quantum technology to unlock their full potential for the industries, we need now to build not only more powerful quantum computers, but we need also to deploy scalable and reliable quantum networks. And really today, it's a delight for me to present to you how Welinq is building the networks that will make quantum technologies a reality for all these industries. So as we gather here today, we believe we are all convinced that quantum computers are revolutionizing all industry verticals. But the problem is that currently, if these quantum computers are taken alone, they won't bring enough computational power to fully deliver for all these industry verticals. Although quantum computing is the only way to solve some of the most computationally intensive problems, for them to fully unleash their power, you need to go beyond single chip capabilities. Because without networking, these quantum computers remain isolated, they remain limited in power. And once you start networking them in a quantum way, there you can create a much larger, much powerful quantum computers. And this is what is really going to make these new revolutionizing technologies solve real-world problems for the industry. And so now, how do we scale this quantum computing? Where we need to build local interconnection between quantum computers at the level of data centers. And Welinq is really at the heart of this by enabling these quantum augmented data centers to connect quantum computers within the same facilities. And these interconnects are essential for scaling quantum computing, and they benefit CPU providers, data centers, but also directly the end users of quantum computing with whom we are working with. But there's also the main application of quantum secure networks, where here we are going to focus on connecting clients securely over arbitrary distances. And here this actor can be financial institution, government bodies, or even any other high security sectors. And here we are going to use quantum encryption to connect securely these users and here partners with whom we are working with to deploy these secure quantum networks are telecom operators, network integrators, but also directly quantum communication testbeds. And so how does Welinq make that happen? Well, at Welinq, we offer the full stack of solutions for quantum networking, covering everything from the use cases down to even the interfaces between quantum computers and the quantum networks that we are building. So let's start from the use cases, and we can take Akadoc, for example, which is Welinq's initiative in the energy sector. Akadoc is the largest initiative dedicated to distributed quantum algorithms. And on the software layer, we have Arachne, which is Welinq's quantum compiler that we have released earlier this year. And this software solution enables to partition large algorithms so that they can run across a network of mid-sized quantum processors, making this large-scale quantum computation possible. And next, we are building the entire optical quantum network. And at the core of this optical network are a specific technology called quantum memories, such as our product, which is called QDrive. And these quantum memories, they act as buffer of quantum information. And this synchronization is key to scale your network, where you can then synchronize quantum communication and quantum computation tasks between quantum devices. And lastly, we have even built the interfaces to make our quantum network compatible with a variety of quantum computers, as these are technologies which are crucial to ensure that the network we are building are compatible with the best quantum computers available. And we are even currently incorporating our solution in our partners' quantum computers. And now I want really to dive in QDrive, which is really at the heart of our quantum networking solution. And it's really the highlight of what I'm presenting to you today. So this product, QDrive, which is our quantum memories, was officially launched just a few weeks ago. And it comes as a result of more than 20 years of research at the intersection between quantum optics and atomic physics, not only to deliver a quantum memory, but a quantum memory with sufficient performance to unlock quantum networking. And in 2 years at Welinq, we have turned this scientific achievement into a real-world, fully-fledged product. This memory is entirely fitting into a 19-inch industrial rack operated at room temperature, which making quantum memory practical and deployable. It offers world record performances with storage and retrieval efficiency above 90% for storage times up to 200 microseconds, which is a truly exceptional fit. And these are critical factors that allow quantum networks to scale effectively. And on top of that, we have several of our units of QDrive which are already being deployed and integrated into quantum networks worldwide. So if you're ready to take your quantum capabilities to the next level, please feel free to contact us to integrate QDrive in your solutions. Now, to wrap up, let's have a look at tomorrow, which are these quantum augmented data centers powered by Welinq. This is the future of quantum technologies with scalable quantum computing and the quantum internet. These quantum technologies need the right infrastructure, and Welinq is dedicated to building it. Get QDrive now, get our quantum networking solutions now, and be part of what comes next. Thank you.
Thank you, Tom. That's amazing. QDrive looks amazing as well as being amazing. So given the work that's gone into QDrive and making it deployable, is 200 microseconds enough? I mean, how far beyond that do you think you can go currently?
Yeah, definitely. So, 200 microsecond storage time is both what allows you to build a local interconnection between quantum computers at the level of data centers, but also allows you to deploy fiber-based, entanglement-based quantum information networks, typically up to 50 kilometers in distance for elementary links that you can send plug one to the other. So that's really already more than one order of magnitude beyond the current state of the art for this cold atom quantum memories that we are building. And we are currently improving the storage time, targeting the millisecond storage time regime.
Of course he's going to say it's enough. Of course he's going to say it's enough. His quantum memory. I think we should go to the end users and ask them, right? I mean, at the end of the day, that's why Tom came, because he wants to know from his potential customers. Chris Janson from Nokia, what's on your mind?
Well, one thing that popped to mind right away, Tom, is I think if I followed you correctly, is you were sort of implying on one chart there about the number of qubits required to do potential usable calculations of some form or another. Now, in my work, and we'll talk about it later a little bit, we're always concerned from the security of the classical network standpoint about cracking encryption on classical networks now. So my question just is this notion of better storage, better quote unquote qubits, if you will, more powerful quantum computers ultimately. Is there an impact of your quantum memory on the potential timeline for a practical quantum computer running Shor's algorithm? So what do you think about that?
That's a very good question, and definitely more than just the quantum memory. With our vision at Welinq is that really quantum networking is drastically going to increase the time to application of quantum computing or quantum technologies. I would say more generally. Let's take an example for quantum computing. If once you manage to network quantum computers, you can limit yourself in the number of physical qubits you can put on a single chip. And once you have that, you can start scaling horizontally. And so this is really a shortcut to practical advantage here.
Daniel Gilks from British Telecom, 200 microseconds. Do you think we are definitely, this is a very good start, but is it enough?
So fantastic presentation. Really interesting to see the work you've been doing. And I guess the question, the answer is a question in itself. It depends entirely on what use case you're looking at. So from a BT point of view, getting to a point where we can start to think about joining quantum computers together outside of a data center becomes very, very interesting. Because as a telco operator, we will probably see some of that data center connectivity as being outside of the internet. That's actually within the colo facility of the data center. So how do we connect one data center to another? Really interests us, and that's probably more where our minds are at. But what is the, what use case we're aiming for? Is it for quantum computer connectivity? Is it to extend the reach of QKD entanglement-based QKD capabilities? Is it to provide an entanglement fabric where people can consume quantum mechanical material around the network for arbitrary and unknown purposes, at which case the timeline you need to know is probably the timeline of the fabric rather than of the individual components. So in my mind, I need to go up a lot of layers from your beautiful technology and understand how it's going to impact my use cases and what I'm going to do with your tech.
Matheus Sena from Deutsche Telekom, what's in your mind?
Yeah, I had a question during the presentation. This is 90% efficiency for, at 200 microseconds, right? Microseconds.
Typically in these quantum memories, the storage and retrieval efficiency is typically calculated at once you get zero delay in these quantum memories. So then you have a decay of the efficiency as a function of time, and this storage time is calculated given the decay of this envelope here. But here typically, with 200 microsecond storage time, this means that you have after 200 microseconds still a good probability of recovering the information after storage.
Yeah,
Tom,
but if you push
sorry, Matheus. Tom, it doesn't get any better than this. We got validation for some of the key end users in the world. Alberto Coming, Airbus, 200 microsecond memory. What's on your mind?
Yeah. Hello, Jose. Hello, everybody. Yes. I think it's a very, very good start. 20 microsecond is very exciting. It was not possible just a few years ago. I would love to see this combined with, say, high retrieval efficiency and also with high fidelity. As Thomas said, sometimes these metrics do not really fit to each other, as you get a very high efficiency or you get a longer retrieval time. I think it would be really great if you go to say 2 milliseconds, still above 90% fidelity. I think that would be really amazing.
Tom, you have 1 year. I'm going to give you 1 year to have millisecond quantum memory. Back to you, John.
Great, thanks, Jose. So to further guide us through this transformative topic, we're joined by Manish Kumar Singh, co-founder and CEO of memQ, a company at the cutting edge of quantum communication technologies. Manish brings a unique blend of deep technical insights and entrepreneurial drive. At memQ, he's leading the development hardware to connect quantum computers over long distances, enabling ultra-secure communication. memQ have developed a solid-state quantum memory-based rare earth dope materials, in combination with integrated photonics. So Manish, welcome to the meeting. Tell us more about these advancements and your extensible quantum network architecture, XQNA. The floor and the attention of everyone is yours.
Thank you very much, John. Hi, everyone. I'm Manish Singh. I'm CEO of memQ. We are a young company in the quantum sector. We are based out of Chicago. As some of you might know, Chicago is also going to be home to a number of quantum computing companies under the DARPA Quantum Benchmarking Initiative. So we are very excited to be here. We look forward to developing new technology that connects all those quantum computers together. So the evolution of quantum computers, as we see it, moves from very small distances, distances that are sub-meter, which we call nodal, to cluster, to campus, and that's campus, and includes data centers, length scales that would be commensurable with a data center infrastructure these days. So going from nodal cluster campus to ultimately a very wide area network, including satellite. And at each of these levels, we identify important key factors that will be needed for the technology to succeed. And you see this evolution of M here. It goes from very small to larger and bolder. This highlights the importance of memory as we go from connecting qubits at a single node to cluster to campus to WAN, but memory becoming more and more important as the distance grows larger. Now, at each of these scales that I mentioned, nodal scale, at cluster, campus, we are talking about different requirements, and then they'll be driven by different factors. These are the factors that we have identified, and this evolution, it will require an extensible quantum network architecture. That's what we are building at memQ. And what we mean by that is a network technology that grows with the size of the network. So right here in this schematic, what we have is quantum memories that are at the center of the entanglement hub. And you have network controls that are present both at this entanglement center and at these quantum compute clusters. And finally, quantum modems that are able to convert quantum qubits essentially from one type of computer to another type of computer to a common language, a common qubit wavelength that's able to propagate over a network. And for that, what we have done is we have leveraged standard fab process. And using that, we have been using commercial CMOS foundry platforms to build up that technology that brings together a lot of these modular key components that remain Telekom C-band compatible. That's the common language we believe that all these quantum computers will leverage to connect with each other over a common network, growing from short distance to really long distances. And for that, our approach has been first, we focused on the component development. This happened over the last couple of years. And right now, we are focused on integrating these components together to ultimately serve systems in the 27-28 timeline. So what we have is a way to leverage 300 millimeter platforms. What we have done with that is we have developed solid state memory capabilities there, control capabilities, and quantum modem technologies that allow us to build the extensible quantum network that I introduced in the earlier slides. So we are very excited to work with the entire ecosystem. And if you'd like to get your hands on these chips, the technology that we have developed, please feel free to reach out. We'll be very happy to work with you. And
Great, thank you.
Thank you very much.
Please go ahead. No.
Oh, yeah. And we are connecting the quantum ecosystem together. Feel free to reach out to me directly at manish@memq.tech.
Great, thanks, Manish. You mentioned you're in the sort of Chicago cluster. Are there what is the current deployment status of the QXNA units? Are there any pilot projects or collaborations where it's being tested and implemented currently?
Right. Few of our chips are out at with different groups where they're undergoing evaluation for their own needs. Chief among them are the control system that we have developed and the quantum memory.
Great. I mean, there's obviously a very large quantum computing company that's going to be based in Chicago as well. I guess that they're also based on CMOS technology. So I guess this is possible route forward for you to connect their fridges together and things like that.
We are very much convinced, and this is something that we share with a number of other quantum companies, is that the interconnect between quantum computers, it's going to be optical. That is the clear path forward. That's the clearest way to connect quantum computers together. And all the development that everybody in the ecosystem has pushed through, all the remarkable development that has happened, especially on the integrated photonic side over the last 3 to 5 years, we have been able to leverage some of that, the ultra low loss waveguides and such, and that has helped us overcome some of these barriers that have typically been associated with miniaturizing photonics.
Great. And what kind of support and services does memQ offer for 𝐋𝐶 implementation?
Right. We are in the process of building out fully integrated systems. So there, would love to understand what the needs of the end users are when it comes to a memory. The memory, as I showed you, it's currently in the form of packaged chips. So if you want to deploy memory at your, say, your research center or a hub that you have where you would like to experiment with that, what is the form factor that you need it in? Do you need it in a box with an optical input output? Do you want to be more involved in the process? Do you want to specify how many memories there are on there? Do you want to specify the level of control you have over that? So we are at a stage where we have done the prototype development. The proof point is there. Would love to work with some of these end users to develop the product that they need.
Fantastic. Thank you so much, Manish and Tom. So whenever designing components for any system, it's of course useful to simulate or model them first. Quantum photonic components are no different. So in the room today, we have 𝐍𝐕𝐀 𝐂𝐕-𝐐𝐊𝐃, co-founder and director of QuantOpticon and president of QuantOpticon Corp USA, and also the principal architect behind Quantillion, a state-of-the-art simulation platform designed to model quantum components with high precision. 𝐍𝐕𝐃, please share your slides. The floor and the attention of everyone is yours to tell us why Quantillion is particularly relevant for the development of the quantum internet. Oh, try sharing again, 𝐍𝐕𝐃. We don't hear you actually if your mic is.
Thank you, John. I'll try to share again just a moment. I
can see it coming through. Yep. And just
it's not in this. Yeah, just
the slideshow button now. Perfect. Great.
Yeah. Well, hello. My name is Dr. 𝐍𝐕𝐃 𝐋𝐶. I'm a co-founder and chief scientific officer at QuantOpticon. We are a software company developing simulation solutions for quantum photonic systems with operations in Chicago, United States, and Guildford in United Kingdom. We are the creators of the first commercially available quantum electrodynamics solver called Quantillion, dedicated for the design and optimization of quantum photonic components, assemblies, and integrated circuits. Our mission is to maximize the quantum performance of these systems while markedly reducing the design cycle and associated development costs. Quantillion is underpinned by our proprietary patented algorithm, consisting of a rigorous and approximation-free theoretical description of the quantum properties of matter and light, which uniquely enables us to make accurate and comprehensive predictions of the behavior of quantum photonic devices influenced by their surroundings. Quantillion can be used for design the bulk of the building blocks necessary for quantum internet, such as entangled photon sources of multipartite quantum states, quantum memories, repeater modules, and other quantum information processing components. It is capable of addressing any atom-like discrete level platform embedded in a photonic structure made of any semiconductor material. Examples of discrete level systems include solid-state qubits, such as spin qubits. For example, silicon T centers, epitaxial quantum dots, and defects in nanodiamond, rare earth element doping, two-dimensional materials such as hexagonal boron nitride, and so on. This could be integrated into photonic structures such as waveguides, micropillar cavities, micro-ring resonators, and more. In addition, we can model probabilistic entangled photon generation in nonlinear materials, such as, for example, silicon nitride. Quantillion is powered by a home-built finite difference time domain simulation engine, providing the freedom to model almost any quantum optical system and in almost any scenario, save the detectors at this point in time. To answer the question what we can do for others, we have the tools to optimize systems to achieve very long qubit coherence times. Another relevant application is extracting non-classical emission from qubits with high efficiency. And we have the know-how to optimize the interface between stationary qubits and photons, and hence significantly improve the fidelity and rate of quantum photon entanglement. Quantillion can serve as a tool of rapid testing of a variety of approaches, configurations, and materials. We can also optimize the performance of remote entanglement links between distant qubits located in separate QPUs. This is really important, as being able to achieve this holds the key to fault-tolerant distributed quantum computing. We are very eager to demonstrate these capabilities. So what you can do for us is to partner with us to co-develop your hardware and act as a feedback mechanism to ensure we deliver the desired accuracy and functionality to reach these goals. In return, what you would be getting is a competitive advantage and a shortcut to highly performant devices. So if you're interested, please reach out to Mirella, and here is her email on the slide. Thanks.
Great, thank you so much, Gabby. I want to understand exactly, what is the unique difference between what your software can do and what maybe an ANSYS or a flex compute can do? What is the point there?
Our unique capability is that we can model quantum phenomena and optimize devices with respect to quantum performance in order to achieve peak quantum performance. And this is what lacks in the current tools. Most of the tools do classical simulations, and separately they use some tools, quantum optics tools, to do the quantum dynamic simulations, but they're disconnected. And what we do is to connect self-consistently classical electromagnetic simulations with quantum mechanics, and introducing quantum description of both light and matter in order to model quantum phenomena and to optimize quantum performance of devices and circuits.
Great. And what are the future development plans for the Quantillion software? What's on the roadmap?
Yeah, most immediately we are working on a novel tool for modeling nonlinear spontaneous four-wave mixing processes in silicon nitride in order to model the process of entangled photon generation and optimize that process on a chip, which we think that it's a route for deployment of entanglement distribution through satellite links as well.
John, you're doing a fantastic job so far. I am enjoying this meeting more than many others. I'm going to ask something to Gabby. Gabby, what this is?
Sorry?
Do you know, Gabby, what this is? Just say you don't know, because it's fine. You don't have to know.
Right, okay.
This is a layer of titanium oxide in which we shoot a laser to change the configuration of the crystal. This is, Manish, allow me to say, this is perhaps the secret of the sauce of memQ. Manish, could you tell us a bit more about this process? Because I think here Quantopticon could help.
Right. Thanks, Jose. This is our way. So one of the most important challenges that every solid state quantum platform faces is how do you make sure where you place your qubits? Because when you're doing solid state qubits and NV centers, it's all over the place. So how do you pinpoint it? How do you place it where you need it? So we use a material called titanium oxide. We use thin films of that we dope with erbium, and these erbium atoms that serve as our memory. The interface between the erbium atoms and the photons that you want to store, that needs to be engineered. It needs to be engineered such that you get very high concentration of electric fields, and you can engineer that using photonic cavities. But you need to be able to also place your erbium atom at the center of these cavities in order for that overlap to happen. And for that, like, we came up with this process that allows you to use laser heating to locally change the phase of the titanium oxide. So you can have erbium everywhere, but if you change the phase locally, what you end up doing is you spectrally move that erbium from the background by about 12 nanometers to one side. So now you can address that small set of erbium atoms directly and not worry about the background at all. So we are very proud of this method that we came up with.
Manish, you should be, because this is perhaps one of the coolest things that we do in the quantum industry, and congratulations to not only for creating it, but also for making it a reliable commercial product. Manish, I'm going to ask you to have a conversation offline with Gabi and with Mireia, because I believe that they can help you modulate. This is exactly what Quantopticon does best. Over to you, John.
Great, Jose. We have a question in the chat from Sarah and Dotra. Sarah, would you like to unmute and ask your question?
All the way from New York.
Yes, hi. I'm from New York. My name is Sarah. Thank you for a great talk. I just wanted to ask if any of you want to answer if entanglement would be scalable and possible over long distances. As I'm aware right now, it's only doable only over shorter distances. So I guess I was just wondering how you guys would think that would be feasible in the future, or if it would be feasible.
Who wants to take that?
I'm going to take it. Yes, Sarah. It will be feasible. That's what we are all here to do. Allow me to continue with the program, because this will be something that we need to discuss further. But of course, having long distance synchronization is perhaps the biggest challenge of our industry. And that's what we're going to do in the coming years with all these people. And that's why BT and Deutsche Telekom are here, connecting with Nokia and connecting with the companies that are doing not only the quantum synchronization, but also the making sure that the data is safe with QKD. I love saying this now. Back to you, John. I'm going to get t-shirts with this.
Okay, great. So we're going to move the program on to another joint keynote from two influential figures in the advancement of the quantum internet, each bringing a wealth of experience and leadership to their respective organizations. Chris Janson serves as the Optical Product Marketing Manager within Nokia's IP and Optical Networks division. With a robust background in optical networking technologies, he focuses on the development and promotion of quantum-safe networking solutions. Chris has been instrumental in articulating Nokia's strategy for integrating quantum-safe encryption methods, such as QKD, into existing network infrastructures. Today, he will showcase a collaboration with LuxQuanta, a spin-off from the Institute of Photonic Sciences, ICFO, in Barcelona, developing cutting-edge CV QKD, continuous variable quantum key distribution systems. Vanesa Diaz's leadership has been pivotal in positioning LuxQuanta as a key player in the quantum communication sector. Chris and Vanesa, the floor and attention of everyone is yours to tell us more about this collaboration between two Optica corporate members that you recently showcased at OFC in San Francisco.
Yeah, thanks. Thanks, John. Let's see if we can get my stuff to share where I want it to share first here. Let me back up a little bit. Anyway, thanks everyone for joining today. It's been pretty interesting so far. Let me give you a bit of perspective to start. Nokia is a large company, right? So what's my interest, our interest in this, and what's the connection with LuxQuanta, I guess, might be on your mind. This, in some ways, is a continuation of a talk my colleague Martin Charbonneau gave in January, I guess it was, in a meeting like this. So I'll spare you a lot of that, but still have to give you a little bit of the background. My interest within kind of a business unit in Nokia is look, we build classical networks. A couple of our customers I see on here, and I see a few familiar names that maybe we met out at OFC. So it's funny. I go to different events sometimes talking about quantum, and everyone likes to focus in on. Sorry about the advances here. I didn't mean that for that to happen. Everyone tends to focus in right on the practicalities of the wonderful things we can do with quantum computers, but the reality is, from the standpoint of a classical network, there also is a threat posed to existing encryption. So we need to be mindful of that, and we're trying to offer technologies that protect against that potential attack. And so, as an example of that, but we could spend all day probably talking about these different technologies. I like to think of how we build quantum safe networks, just real broadly in terms of some of the cryptography that's involved here, as ways to lock down information as it traverses a network, ways to create keys that are extremely safe, and then ways to distribute those keys among endpoints. And so a bit of a precursor to what Vanessa is going to talk about is this idea of using quantum keys and then distributing those keys via a symmetric mechanism to existing cryptography. So this particular picture that I show here, this is a general model for what we call our quantum safe networks, where we see a change right now, a shift in networks in the way we actually protect things. From protecting strictly maybe at one layer, like the optical layer, or protecting it at the IP networking layer, or perhaps up at the application layer as well. But a number of technologies that are emerging right now will find a strong place within ultimately what we call a quantum safe network. Now, the way that actually gets implemented, to direct your attention really to the center of this slide here, where perhaps we have a symmetric key distribution mechanism, and we automatically throw keys out via classical means, classical networking means, to either optical transponders or IP routers or whatnot. But what's most interesting here, perhaps, is kind of up at the top here. This is really a quantum network in a sense. This is a QKD distribution mechanism over what we might think of as the first practical implementation of a quantum network. I don't want to say quantum internet, but it's stepping in that direction. And so what Nokia have done is kind of at this point in time, demonstrated and positioned ourselves with companies like LuxQuanta to demonstrate and develop into a commercial product, QKD, as an overlay to this automated pre-shared key protection mechanism. And there's different advantages of that, which I don't need to get into right now. But ultimately, again, I think of interest to this audience most might be how QKD forms really that first example of a practical quantum network. So I guess I'll leave it at that for right now. And Vanessa, I'll hand this to you. Let you talk about what you're doing on your side, from LuxQuanta's side.
Let's do that. Chris, it's always a pleasure to share the work together. So I'm trying to share my screen. You're gonna have to help me. Let me know when you can see it.
Okay.
Okay.
There it is.
All right. So what have we been doing, as Chris has introduced already? By the way, I love listening to everyone contributing with the wonderful technologies that we are developing collectively to enable this super quantum internet. The stage we are in, we don't have enough capacity in terms of quantum speed, so we can send everything over there. You guys are actually doing wonders already with what we're capable of. What we can definitely do is just to use the small bandwidth that we have available to exchange cryptographic keys, and so we can encrypt the information above. So the work that we've been doing with Nokia, that by the way, not only has been extremely useful, but also we always have a blast working with these guys, is among other things, is just narrow it down to the different use cases, different scenarios, because as Noel was mentioning at the beginning, each vertical, each type of customer has different requirements. So one of the most, I would say, juicy places to start with thinking about how quantum key distribution can help is data centers, because across the world, they've been started to be considered by the governments as critical infrastructure right next to electricity, water, and so on. This is a very rightful day to talk about it, in fact, because yesterday in Madrid and in Spain in general, we had a massive blackout, and the impact of that was huge. We are so vulnerable. Data centers host our most precious information because everybody has all their data some way or another in one of these buildings. And at the end, those buildings are connected to the rest of the network using optical fiber. That is something that it can be tapped and the information can be extracted. Maybe for later on when quantum computers are ready, maybe when artificial intelligence gives birth to something that cracks the cryptography as we know it today. So to protect the information in transit, we can use this little bandwidth to send the cryptographic key. So quantum key distribution is hardware, same as many people here today in this code. So we sell 2 units, a transmitter and the receiver. And then what we do is just plug it with a quantum channel that is going to carry the cryptographic key coded in the light and very attenuated. So it responds to the laws of quantum physics, so we can do some magic, the one that Einstein said it was impossible. And then we need another channel for the 2 machines to just agree on what the keys are going to be, to pass it on to the next layer, the key management system, and so on, to the encryptor, the switch, the firewall, whatever application is going to then use this keys to get encrypted information and make sure that it's truly future-proof for years to come, no matter you hit this technology with a quantum computer with 5. So what is it that we need for this technology to be widely deployed? Because what we are seeing right now is many of the customers that have been acquiring solutions from LuxQuanta, they are thinking in terms of this point-to-point, very simple kind of link. But what we want to go is to a place where this is widely adopted. It's actually happening as we speak, but we want to incentivize that. So we have a saying in Spain, bueno, bonito, barato, which the translation would be good, pretty, and cheap. That would be the best product to sell. And that's where we've been working towards at this time. So let's talk about some of the things that can make already quite impressive technology a very good product that we can sell. So let's talk about fiber consumption. That is the most precious resource and the most expensive in optical network. So the fact that we are working, LuxQuanta is working since its birth with a new flavor of quantum key distribution, is the new kid on the block, and it's called quantum continuous variable, QKD, is that we have crafted something out of that protocol that allowed us to have only one optical fiber as the quantum channel to send the information. And then another extra link that it can be just a copper cable connected to the public internet for that post-processing channel. This is highly appreciated because at the end, again, it's the most precious resource, and in many places of the network, we don't have the luxury of enabling more optical fibers. This is so you can see the direction that we're going, right, with this technology. The other thing that we can do is not only we need one optical fiber, but also we can have the data right next to it, the quantum channel, and vice versa, in the C-band, not somewhere else in the attenuation spectrum of the optical fiber. This is a concept that, although we've been repeating out there in the industry for now 4 years solid, it's still not that simple to understand. And this means that most of the optical communications take place where attenuation is the lowest in the C-band. So it's an ideal place to just craft right next to the data, the quantum channel, and then you don't have to enable any other band that you potentially might not like. So this is unlike what the older version of the technology proposes. Either I put the quantum channel in the O-band, and then the great performance that these guys can deliver, it is diminished, or then we can have the technology or quantum channel living in the C-band, but then I have to move the data. At the end, the boss is the final end user, whether it's a data center, a financial institution, or a telco. And this is something that, depending on their needs, is going to be more or less appreciated, but definitely is a feature that makes continuous variable QKD extremely unique. It's something that makes the technology very distinctive. So with these things, lean use of optical infrastructure and also coexistence in the same optical band, we keep working towards making the solution even easier to deploy. So enabling configurations that were not so common other in the industry and not for all the manufacturers. So what you're seeing is the common point-to-point link where you have like a daisy chain with transmitter and receiver. One of the things that we are doing with our technology, NovaLQ, is also allowing for a point-to-multipoint configuration where you have one transceiver and multiple receivers. So this is what you just seen that right there in the schematic is a demonstration, for example, that we did recently with Telefonica connecting 2 hospitals across the city of Madrid. And what you're seeing on the other side is another deployment that we've done with a telco here in Europe, where several receivers were connected to the same receiver. Why is this very valuable? Because you can enable one extra node in your network for half of the price. So every time we've been selling a pair of our beloved NovaLQ easily, we see these customers coming back for more receivers to enable more points in the network. So this is just a bit of a glimpse of everything that what we've been working on to make sure that our product is good, pretty, and cheap. You can tell that it's pretty, by the way, with this slide. This is the second generation. So 2 years after our first version, we worked extremely hard to remove one of the barriers that this new kid on the block or continuous variable QKD had at birth, and it was at maximum distance. I saw you, Jose, now typing there, is 20 whopping dBs enough? Let me tell you, we haven't finished with this just yet, but it's already an enormous amount of power budget to spend and cover the place in the network where we are shooting at, where you have the highest number of connections and nodes, and therefore you need something that is like a 4-wheel drive, and it's very efficient in terms of cost, the total cost of ownership. So this is the latest and greatest generation that we released at Mobile World Congress this year, and it's making the most of continuous variable QKD. All the components are telco grade. We can apply economies of scale. It integrates into existing optical links as well, dirty optical fibers, something that is very common if you go to the cities to deploy this. A very lowest cost per key, because at the end the key rate is very high, so that allows you to feed multiple applications as you keep loading them with the keys from these devices in the same optical node. And there's these coexistence capabilities that we can deliver even in the most tight conditions. You can shoot us with dense wavelength division multiplexing, where you have just narrow channels. We can squeeze our quantum channel right there. And then what we've been talking about, we can operate anywhere in the C-band and enable multiple configurations, even exchanging units. And last but not least, all this work in the industry, selling to all these different verticals, has allowed us to also make great friends, not only Nokia here today, but also leading manufacturers in terms of key management system that we also need, so you have a glimpse of there. So what we've done with Nokia is a demonstration where thinking about, back to the beginning, data centers, critical infrastructure, just showcasing something that is just bringing together some of the things or features or hardware that collaborates beautifully together. So this is a demonstration that it was done last year towards the end of 2024. You're seeing the layout. So we were protecting the communication to the data center provided by Digital Realty, with Lyntia operating as a customer with 2 more data centers in the city of Madrid. So what you see is just 2 steps, and this is something that I love highlighting, the fact that we have their beloved competitor, quantic. So they were protecting a part of the jump, so to say, to get to longer distances, whereas we were covering the first chunk of the connection. And this is where you can see how this technology plays. So the coexistence is showcased here because we have the optical link that was existing. We were inserting our quantum channel right in between. But not only that, that optical fiber, it wasn't a standard G.652D fiber. That is a hollow core, low latency fiber. And this is where it gets very interesting, because this type of fibers have very low latency, and they are highly it's highly appreciated by data centers because they can play around in the financial world with those little differences. So this was kindly land for the project by OFS. That's the fiber that came from. Also, we had another partner of ours, Evolution Q, with the KMS. So it was a huge success, and it was a demonstration that even though quantum key distribution exists for quite a few years, We're still learning on what each different vertical, in this case, data centers, can make the most of it. It's definitely a great point of the network to start with, because this is where the pipes are carrying the most amount of information, sometimes extremely delicate. It's a very great starting point, and that's how we are posing out there. And this is what I'm telling here to the industry, anybody listening to us. If you have in mind any kind of data center that you want to prepare for the quantum era that we have already started in, we are definitely the partner. We've been in the industry now for 4 years. We are already product ready, and we are a European manufacturer as well. Also, this technology is field proven because we've been deployed. This company, its revenue is multi-millions, several millions. Actually, we've been hitting our sales target consistently, and we've been deployed this with many different verticals, from, of course, governments to telcos, data centers, and even financial institutions. And also, I think it's a company that I think we're very proud as well of the team. We are 34 people now and growing, extremely smart, very happy to learn and see how we can make the most of this technology for your needs, because at the end, again, the customer is the boss. Thank you.
Great. Thanks, Chris and Vanessa. So, Vanessa, data centers are huge, geographically huge centers. In terms of the Nova LQ system, what is the limitation? How many systems do you need to keep an entire data center secure?
It varies, because if we think about hyperscale data centers, we could be talking about it just only the hyperscale itself, a few dozens. If we think about different business models, like, for example, think about a data center in a city where different customers are connecting to. In that case, perhaps each customer rather having their own pair than sharing. So there are multiple scenarios. But if we really scale this to the world, we're talking about thousands of UKVs. So again, one of my concerns is not whether this takes off, is whether we will be ready by the time everybody starts getting restless.
Great. And I asked Noel the question about scale. In terms of your rack mount system, is there a plan to scale those down in size? Can you see a world where they're actually inside a pluggable
Oh yeah,
system?
that's the dream. I mean, eventually, I love to have, for you all, for myself here at home as well, one inserted in our router. We're working towards that, but definitely we're being very practical and delivering first what we know the industry needs first. So this is why we are having, for now, this 2U high that is also a record in the industry. This is not something that I just say, everything together, this 20 degrees, this form factor, this performance is right now is the best in this flavor. But we're working towards making it even pretty, even cheaper, and even easier to install.
Great, thanks. And Chris, coming to you from a Nokia perspective, how widely adopted are you seeing quantum safe solutions today? And what can Optica, the Optica network, do to help you kind of make it more widely adopted?
Well, look, I mean, your second question first, Optica OSA formerly, I think of, you guys give us that visibility and channel into, that bottom layer of one of those slides I showed you earlier, obviously the optical network. So that's big. I mean, I view as helping us touch our customers, especially in the, service provider realm, but as well, every other type of network operator. So how many customers do we have operating quantum safe networks today? It's actually much larger than you might think. Now, I want to make clear, because I know I went through those slides pretty quickly, I want to make clear that QKD, the use of QKD does not necessarily equal what we call quantum safe. In other words, there are other protections that we tell our customers they could put in place now that afford protection. And that's this whole idea of symmetric key distribution. So then we layer on top of that QKD as preferred for various reasons, which we don't need to get into right now. But so anyway, that number is in the hundreds, maybe several hundreds, okay, where we have customers that already are using encryption and may or may not recognize or may not already be using symmetric methods for key distribution. And so there's a little bit of an education process going on right now where we tell our customers, okay, you've got an optical network. Are you encrypting? Yes or no? Do you have critical links encrypted? sometimes not. Sometimes they have the encryption engines there, but they haven't turned them on and licensed them. So there's all these different scenarios that have been playing out over the past few years. But what I can say is that we increasingly hear that people are aware of the issue, and that they need to be taking action. And so, you know, we leave it at that. It's really been evolving quite quickly over the last, say, 2 years or so.
Great, thank you so much, Chris. And we're having so much fun. Time is running away with us, so I'm going to move on to the next speaker. No, my fault. So it gives me great pleasure to introduce Daniel Gilks, a leading voice in quantum communications and head of quantum strategy at BT Group. Daniel has been at the forefront of BT's efforts to translate quantum theory into real-world telecom solutions, from shaping BT's involvement in national and European quantum projects to steering partnerships that integrate QKD and quantum-safe technologies to live networks. He brings technical insight and strategic vision for what the quantum internet means for our digital future. Daniel, please tell us more. The floor and attention of everyone is yours.
Right, let me see if I can sort out my my presentation. I'm going to become blind, so from this point onwards, I can't see you guys. Can you hear me and see things?
Yes, thank you.
Excellent, thank you very much. John, thank you for the introduction. I'm going to need to get a playback of that. How did you put that together? Jose, John, thank you very much for inviting me, and thank you for giving us the time to talk about what worries us in BT, what keeps us occupied in BT, thinking about what a quantum internet is. I just would say at the beginning, it's really, really impressive to see the work that's ongoing in the community from hardware providers, system integrators, the amount of development, the speed of change, and the ambition that's being shown is really, really impressive. And I'm going to stay away from that for today, mainly because I think that there's clearly a really rich and vibrant ecosystem of people bringing technology and platforms and systems together. And in some ways, the operator's view is kind of more around translation into deployment, into use cases, into customer propositions and abstraction into an internet. And that's where I'm going to focus more today. So the first thing I wanted just to show is some stated policy, horribly paraphrased from the UK government, which is the UK government's 5 quantum missions. Mission 1 talks to having accessible UK-based quantum computers. Mission 2 talks to having an advanced quantum network at scale, pioneering a future internet by 2035. Mission 3 talks to NHS trusts in the UK, benefiting from quantum sensing. I've grayed out Mission 1 and 3 because I don't think they're directly areas that BT has a huge play in. Mission 4 is around navigation clocks, deploying navigation on aircrafts and providing next generation accuracy independent satellite. And Mission 5 is around quantum sensors for critical infrastructure, transport and telecoms. Now, when I look at this UK government position, aside from the fact that this means there's some funding available and there's some research direction being set here, it kind of occurs to me just how much of this lands in the lap of telecoms. Supplying networks and internet in the UK and abroad is going to come down to telco operators delivering a platform alongside the community on this call, looking at how we deliver clocks outside of satellite is a huge opportunity and challenge for a telco infrastructure, which needs a synchronization and needs timing dissemination in its core, and how we use and support quantum sensors within the telecoms infrastructure. That's straightforward. It's in the telecoms infrastructure. So whether telco wants it or not, quantum technology is going to come and be a huge impact in our way of working. And I think that's recognized now globally in telecoms, but it's also throwing us challenges. And I think that's been touched on already in the calls today, that actually that's going to change the way telcos operate and the way we understand technology, the way we integrate technology. Now, while quantum technology has the added cachet of being super hard, super interesting tech, physics and material science, as we've seen throughout all of the discussions today, actually lots of telco equipment already has a lot of those properties. We're already running high performance solid state lasers at scale. We're already running complex protocols. The way an internet works for an operator is to do with abstraction and how you box those challenges up and actually wrap them in something that you can deal with. So on the one hand, from our BT research perspective, we're working with our colleagues in security and networks and the corporate entity of BT, to understand what quantum technology is for us and how we integrate it into our business. What I want to see perhaps more from the ecosystem is how do we get to that stage of abstraction, which means that what's being developed in all of your respective companies and capabilities becomes something that a network of networks spanning the globe with various use cases and various different use case challenges can start to consume. And I think that's what I need to see. It was really interesting to see in the LuxQuanta Nokia presentations, the combination of EvoQ with different QKD systems. And I think that kind of infrastructure is what we really want to see and need to see across all parts of a quantum internet. So I just want to give a little bit of a background on some of the quantum activities we've been working on at BT for the last few years. Our kind of big shareable network platform that we've been running is our quantum secure metro network, which has been in partnership with Toshiba's hardware, HSBC as an end user, EY have had an involvement, and we did at one point have a portal on AWS, and that is based on a network architecture that's not too dissimilar from the Nokia LuxQuanta described model, although for us our underpinning is a DV-QKD system, and we work with Toshiba. In that, we've had 3 running core nodes in the UK, 1 in Slough near our data centre region, and 2 in the City of London that give us access to the business districts, financial districts, legal districts of the UK. And that's been a really interesting piece of work. The technology that's been brought through by technology providers such as Toshiba is excellent, and it gives us routes to think about supplying a QKD proposition to our customers. Whether the long-term evolution really is that one customer wants QKD in their own premises, or whether what you really want to do is serve QKD distributed at a colo through a variety of key consumption, a MACsec and IPsec kind of variants, I think is still open. What the cost points you'd have to look for and how you deploy that is an interesting challenge. And how you break out of a small geographical range, I think, is still a challenge. So in the previous discussion, there was a question around whether 100 kilometers is enough. I think for us, for a point-to-point link, 100 kilometers is enough, but that does not make a key fabric. We need to see a national and then international scale key fabric, which supports customers across a geography with range, with access to the key material they need when they need it. And to some degree, that's going to involve an awful lot of network protocol thinking and other pieces of network fabric consideration around how do you sparsify key material for different users across a multi-noded network. How do you reduce the end user cost by being able to serve multiple customers from the same hardware? Or is that not something that has an appetite? Or do you look for those customers that are prepared to put high value equipment in their own premises just to offer themselves some differential security? I'd echo the kind of view from Nokia around wrapping post-quantum crypto and different crypto agility into a quantum secure proposition as being our entry point, probably from a QKD point of view, rather than what you want as a product is necessarily QKD. We're still toying with that shaping as to what the customer presentation is and what customer wants. But that's a really big piece of our quantum program, our quantum work to date. That's flushed out an awful lot of challenges in network integration, not just getting the boxes, getting them into the network, but also things like how do you assure a technology that you're placing in your network and saying this object offers network security. If you are going down that route, how comfortable do you have to be in the way it's hardened, the way it's built, the way it's deployed? How do you build the hooks into a network operations center to deploy a scale quantum network? How do you manage the workforce to be able to actually uplift and keep that system running? But so that's had a major piece of our quantum program. We've also, at the moment, we're running an Innovate UK project called QAssure, which is a UK-based consortia looking at accelerating the assurance for quantum secure comms. That's given us a really good breadth of collaborators, but also it's allowed us to dip into the ecosystem of different universities, suppliers, collaborators that can help us in this space. Being UK-based, we have a really strong exposure and interest in using Innovate UK as a vehicle for collaboratives and for collaborative cooperation with customers and industry partners in our jurisdiction. But actually, in some ways, as discussion said today, it's not a UK challenge, it's a global challenge. And actually, Innovate UK is not helpful in terms of having global reach in that way. So we're quite glad to be back in our Horizon Europe funding opportunities, and we need to figure out how we use that best. In the meantime, we've just had a few successes in the UK pilot calls that have just come out from a quantum point of view. So we're going to be looking at entanglement enhanced quantum integrated networks with Toshiba, University of York and HSBC. We've just closed a project called Quantum Data Center of the Future, where we worked with Orca. I'll wrap up here. So we've also been doing a little bit of work on, doing a lot of work on RF sensing using Rydberg atoms and how we would build a network entity for doing RF detection and down conversion using rubidium systems and red and blue lasers. So what I would just point out here is that in our research facilities, we're happy to work from quite close to a university optical table up to something that looks 19-inch rack. That changes for us because in our BT infrastructure, our research facility is quite separate from our network platform and architecture structures. So we're able to work outside of things being 19-inch rack only. We like that model, but we also can work with things that are before 19-inch rack integration level. Has my slide just moved on?
Yes.
Thank you. So what I wanted to challenge the room to think about in general is how big and how broad can the concept of a quantum internet be? So I think what we've talked about a lot today is probably the top line here. So it's a network which allows quantum state transport, you know, with entangled transport in and out of quantum processing objects, whether they are quantum computers or logics or sensors or functions or memories or repeaters. And in my mind, they're kind of logical entities in a quantum network. And that becomes a way of providing either quantum security through QKD, or it becomes a way of offering scaled and scalable quantum computing. But I think for me, if I was thinking about what BT wants to offer in the next 5 to 10 years, I want it also to just be a network resource that provides entanglement. So if someone can just take and consume entanglement at the layer of an entanglement fabric, that then means that I, as a network operator, don't necessarily need to know what that user is using the entanglement resource for. I just provide it because as a network operator, it's my job to provide various exposure layers to physical transport application layers in my network and provide resources to other users. So I kind of think it's important that we, as a community, build a really clear sense of what the use cases for quantum network, quantum internet are as a homogeneous whole entity, but also build out the abstraction layers and understand what it is one user or another might wish to come to this network stack to consume. And that isn't always full application layer, and it isn't always about the technology. So the third bullet point, obviously, we've talked about a lot in this call, but there's a desire for quantum state transport for quantum security. But I think it's also important in the next few steps just to think about what are the quantum ready classical underpinnings. If you've got 200 microsecond storage of photons in a rubidium memory, then at the moment, where does that sit alongside the timing precision of a core network? Where is timing exposed in our network so that a quantum memory can consume that information when it's making decisions to retrieve, switch, or perform actions upon that memory? What structures and systems do we need in a quantum internet to give us hyper-low loss if we want to distribute photons around a network? Do we actually want to work with a standard telecoms fiber and infrastructure that we have today? How do we escape around things like EDFAs and DWDM filters if we need to? So I think there's a whole load of infrastructural and architectural bedrock there around what is the classical network looking like to allow us to actually embed quantum technologies, and also how do we kind of harden the network that we have to make sure that emerging network quantum technologies can coexist, or ideally could a quantum internet do all of the above? And to that end, I doodled a little doodle, but in my mind, an internet is a network of networks. lots of the components that have been talked about today are hugely important for pulling together a network capability. But an internet has to be more than just a network. It has to be my network can talk to your network. Customers can interact with the different layers of a network, whether they want to be an application layer consumer or whether they actually want to interact with a fabric structure and just take keys, for example, or just take entanglement. And we need to think really carefully about the wide underpinning of classical components and quantum components that build that structure. And I know that there's been so much really impressive content today around all layers of this infrastructure. But to me, a quantum internet has to be more than just quantum networking. And that's what I would like to think about more in terms of BT's aspirations, is how do we build a multi-vendor, multi-jurisdiction, multi-operator infrastructure that clearly underpins use cases, customers, and applications at the application layer for wider benefit. From a more parochial point of view, as a network operator, anything that allows us to see embedding technology into our network and the network being relevant is hugely valuable to us. For the last 10 years, I think a constant challenge that the network operator has had is it's become a supplier to an over-the-top market where someone else has taken the large amount of customer interest and value. So if we could start embedding QKD relays, quantum memories, and quantum entanglement in our network and make the network the shining jewel again, I think that is of huge interest to the operator community and certainly to BT. I think from me, that's kind of where I'm at, which is too many thoughts. Yeah. Huge appreciation for the amount of things you've shared with us today, and a need to build an internet rather than networks.
Daniel, thank you so much. You've given us a lot to think about from a end user network operator point of view. We're going to have to swiftly move on to the final keynote of today, which showcases a collaboration between Telebit, SPA, and Optica corporate member and meeting sponsor ThinkQuantum to advance quantum secure communication technologies, focusing on the practical implementation of QKD systems. So we're pleased to introduce Daniele Satarato from Telebit and Costantino Agnesi of ThinkQuantum, two leading figures in the advancement of quantum secure communications. Their recent notable collaborative field trials have provided valuable insights into the practical deployment of QKD over existing telecommunications infrastructure, which is critical for the scalable and cost-effective deployment of the quantum internet. Daniele, Costantino, take it away. The attention of everyone is yours.
Okay, thank you, John. I will start, and then Costantino will follow. Good morning or afternoon, everyone. It's a real pleasure to be here today. First of all, let me thank you, the Optica team, for the opportunity to present Telebit, the story, the values of the Telebit group, but also our commitment in going through this new quantum era. Let me give you just a quick overview of who we are. We are the Telebit Group, a system integrator in Italy with solid expertise in ICT, telecommunications, technological system, and electric mobility. Our team is made up after 1,800 professionals, skilled, creative, and driven by an entrepreneurial spirit. We're not just solving problems, we're working toward ambitious goals. Thanks to our consistent growth strategy and a secure financial base, we try to reinvest all profits into new opportunities, including extraordinary expansion. But what truly sets us apart in our foundation of strong human values and a long-term vision of sustainable development. Telebit was born about 35 years ago, and our experience is based on a merit-based network of reliable partnerships with 27 offices across Italy and 4 in Brazil. In 2024, we surpassed 300 million euros in revenue, which is a result of passion, innovation, and trust. Our mission is to design and maintain advanced networks and systems that can connect people and things in a seamless and secure way. Our vision is to be a national benchmark for quality and expertise in technological infrastructures. We can go now, please, Costantino, with the next slide. Thank you. For the Telepit Group, cybersecurity and advanced networks integration are not just part of our business, they are pillars of our identity. In our experience, protecting critical infrastructures are not what we're looking just today, but it is useful to prepare the tomorrow's challenges. We are actively investing in quantum secure communication, trying to anticipate the quantum revolution and its impact on data protection. Our expertise in QKD allows us to deliver customized, high-assurance solutions for key sectors, such as defense, government, finance, and data center operators. But how he said, innovation doesn't happen in isolation. That's why we led internal training programs to build in-house quantum expertise. We collaborate with top research institutions and conduct real-world proof of concept trials. And one will be presented with Costantino later. We also work closely with technology leaders and participate in standardization bodies to help shape the future of secure communications. Try to reassume, we are not just following trends, we are trying to help set them. Through partnerships, education, and market engagement, we are committed to making quantum security real, practical, and impactful. Perfect. While quantum technologies hold enormous promise, we at Telepit are fully aware of the current limitations in the QKD market. Today, the technology is still in its early stages, and that comes with real challenges. We have saw with the brilliant presentations that came before me such challenges. High implementation costs and the lack of scalable quantum repeaters mean that most deployments are limited to simple point-to-point connection or maybe star topological networks. So it's a big constraint. Complex architectures like mesh or multi-node networks are not yet practical due to signal loss and infrastructure constraints. As a result, QKD is currently viable only for a small group of clients operating in highly security-sensitive environments, such as military institutions, government agencies, financial networks, and data center interconnections. In this context, the most realistic use cases today focus on encrypting data over short distances between a few critical nodes. That's why our strategy is focused to serve these high-value sectors with tailored solutions while actively contributing to research and innovation that will help us scale the technology in the future. That is, the strengthening quantum security isn't just a technological challenge, it's a strategic imperative. As we move toward a hyper-connected world with AI and increasing demand for bandwidth, future communications will demand protection beyond what classical encryption can offer. And that's why investment in research, development, and field trials must be a priority. To unlock the full potential of quantum communications, we think we need to tackle the key technical barrier, extending QKD over long distances, reducing the reliance on dedicated fiber, improving key generation capabilities, and crucially, lowering costs to enable broader adoption, which is, I know, linked to the capacity to sell. This transformation requires a coordinated action. Increased capital investment is essential, along with the smarter public funding mechanism tailored for the real needs of the quantum ecosystem. We need a clear national and European roadmap with measurable goals and strong governance to scale up both domestically and internationally. Finally, we must raise awareness not just of the threat, but of the incredible opportunities quantum technologies offer. It's time to act. From my perspective, the harvest now and the crypto later theme is something that is hard to make feel by the client. Telebit is trying to act as a strategic bridge between research and development on one side and the institutional and regulatory frameworks on the other, serving as a system integrator that connects innovation with the implementation and helping to build a unified value chain between the market demand, the technological supply, and public policy. Okay, thank you for your attention and opportunity to share Telebit vision. We believe that meaningful progress happens through collaboration. And that's why we're proud to work alongside key partners like ThinkQuantum, with whom we're actively conducting field trials to turn innovation into reality. I'll now hand over to Costantino from ThinkQuantum to dive deeper into the technology and ongoing initiatives. Thank you.
Thank you, Daniele, for contribution. Just let me start by spending a few words on thanking John, Jose, and the Optica team for their excellent job on organizing these events. It's always a pleasure being able to sponsor such a great exchange of knowledge in quantum, internet, quantum communication in general. So let me begin by introducing ThinkQuantum. So ThinkQuantum, we're a hardware company, and we develop cybersecurity solutions that are based on the laws of quantum mechanics. We were born as a spin-off of the University of Padova in Italy, and due to this, we have inherited a strong scientific background and a strong spirit also to innovate technologically. And this is what basically has propelled us in the development of what you see here in my slide at the upper right corner of a slide, our current product line, which is the QKD platform, which is our QKD quantum key distribution platform, and the ThinkQuantum, which is our quantum random number generator. And these two devices basically are what allow us to work actively in the development of national and European quantum key distribution networks. And interestingly enough, we're also working not only in the terrestrial aspect of quantum key distribution and quantum communication networks, but also we have a strong expertise towards the space domain with several initiatives developing both satellite payloads and ground stations. But today, in this presentation, I'll focus a bit more on our QKD device. So our QKD device is a polarization of encoded BB84 QKD system. It has integrated inside of it a quantum random number generator, which basically allows us to have each qubit that is emitted coming from a random, fresh random number directly from our ThinkQuantum. And it basically has a few aspects that make it quite interesting for system integrators. that I would like to highlight. The first aspect is basically the way that we synchronize our QKD system, our transmitter and our receiver. That is a bit different from what is usually found in other QKD systems, because here we basically just utilize a single fiber for everything. So we use a single fiber to do the quantum communication, but also the service channel to synchronize the transmitter and the receiver. And how we manage to do this is through the use of the qubit for synchronization algorithm, which is something that we have developed, which allows us basically to use the same qubits that we are emitting for quantum key distribution, also to have the information required to synchronize the frequency and the absolute time between the two devices. So this is basically comes with an advantage that you don't require a couple of fibers to allow the communication between a transmitter and a receiver, but you're able to do everything with a single fiber, which is quite useful, especially in scenarios where fibers could be scarce. The other aspect that I wanted to highlight is that our cookie systems are quite flexible in how they can be integrated into a quantum communication network. In fact, they are very versatile. For example, when you're trying to develop either a star or a ring topology, and this comes from the fact that we are utilizing polarization encoding to encode basically the quantum information, which gives us a very strong advantage, since this allows us for each Alice and Bob to be absolutely versatile, since it does not have to be optically matched with its partner. Any Alice and any Bob developed by ThinkQuantum can work without requiring any calibration of any sort. So this, for example, is an interesting thing that we can do, because as you know, in many quantum communication networks that are under development right now, this is a topology that you often see, which is basically the trusted node scenario, where basically you have want to connect point A with point C, but since the distance is quite long, you need to pass through an intermediate point, node B. And often what you see in these types of scenarios is that you have basically two couples of QKD systems, so two transmitters and two receivers. The fact that we are able to basically intercommunicate with any other device that we have developed allows us to change a bit this scenario. This is because we can exchange one of the receivers with an optical switch. So basically, we change the scenario to something that is depicted in this figure, where you can basically see the transmitter, the two transmitters that we have talk to a single receiver. And basically, we're doing at time multiplexing, where some of the time is allocated to the first transmitter, and some of the time is allocated to the second transmitter, which is, let's say, a very cost-effective solution to solve the same issue. And this is cost-effective, especially because, first of all, you're reducing the number of devices that you require from 4 to 3, but also, most importantly, because we reduce the number of receivers that we require to just one, and the receiver is basically the most expensive device among the two. So basically, having shown these few features, I can now highlight the work we have done, and we're proud to show together with Telebit, which is let's say an initial integration of our QKD systems in a deployed fiber that link two cities in the Veneto region, so very close to basically both ThinkQuantum and Telebit, since they connect Treviso and Venezia Mestre. Here you see the link was around 20 kilometers in distance. It was a deployed fiber with traffic. It's a bundle of fibers with I think most of the fibers already occupied for classical communication, basically for a network traffic between Treviso and Mestre. But we had a fiber that was allocated for quantum key distribution. And interestingly enough, this scenario was also interesting from a scientific point of view because there were two different type of fibers, so two different standards, the G652 and the G655, that we could test in parallel. So these two different standards of fiber ran exactly along the same route. And we managed to basically test in parallel the performance of our QKD system in these two different deployed fibers with different standards. What we saw are basically very encouraging results. And you see in the top right, the average, the quantum bit error rate that we observed throughout the whole field trial, which lasted one full day. And you see that the quantum bit error rate never surpassed 1%. So basically, we had an extremely stable quantum bit error rate in a deployed fiber over 20 kilometers. So this basically attests that the buried fiber is an extremely stable channel, especially for polarization encoding. And in the bottom, you can see basically the secret key rate that we were able to obtain. The secret key rate was basically what we expected with the G652 having a bit higher security rate, but this is fully explainable because of its lower loss per kilometer profile with respect to the other standard. Apart from doing, let's say, just a QKD field trial, we also did a co-propagation experiment where we had both classical channels and the quantum key distribution signal traveling on the same fiber. With these details, you can find on the publication that I linked here in the bottom of the slide, and I omitted for brevity. But basically, the take-home message is that the QKD systems are quite robust and are fully commercially available, and basically together with a partner such as Telebit, but also, British Telecom, Deutsche Telekom, we can definitely start not only showcasing this technology, but proposing this technology to potential clients, because we certainly believe that the technology, at least for quantum key distribution, is mature. The use cases are existent. What we now need is sufficient visibility with potential clients to make this type of technology not only used in proof of concept experiments, but in real world deployment, real world applications. And with this, I would like to thank you again for your attention. Thank you, John.
Grazie mille, Costantino. This is a fantastic deployment. Thank you very much for showcasing that here. I would love to have this round of clients now so they can evaluate it. So let me start quickly. Chris Janson from Nokia. You have followed the conversation clearly, and I also know that you are very well involved, as you told us, with the QKD sector. What advice would you have for Costantino on his development?
Well, there's a couple of really interesting things there that caught my my attention, especially the single fiber aspect of that. And look, the reason I say that is having been involved in a number of demonstrations set up in QKD, and it's often tempting to just say, okay, there's a Q channel up here, a couple of things to plug in, a couple of things to configure through a DCN, and the complexity of that can often, you know, be kind of lost in the planning cycles, and then until you actually go to deploy this stuff. So I found that pretty compelling, pretty interesting. I think I think partnering with a company like Nokia, I don't know if we've worked together, Costantino, yet, but I think that might be helpful. Just saying that. Having a closer connection, perhaps, to classic network equipment vendors could be helpful as well. So, yeah, there's a couple of things that popped to mind there.
Thank you very much, Daniel Gilks from British Telecom. You have seen that they use a unique fiber for the two. Is that something that you find exciting? What is your vision for this kind of QKD? Daniel, yes.
I'm just coming off mute. Yeah, so I think from our point of view, we want technologies that feed into our future QKD network as it stands. which fibers particularly they use perhaps is not so important to us, because we would look at how we build out a fabric. But what I think is really important is to get close to either a vendor or an operator and really get your head around the integration stages that are needed to be in a customer's premise, how you're able to be in a live network, and how you fulfill things like TSA for the UK, but other national regulations around technology. Think about that getting into live, and I think that echoes what Chris said about getting close to Nokia. Nokia would help you with that. BT would also be able to explain some of those steps to being a live operation tool.
Matheus, send us home the way that we deserve it. Here you have your final statement of this online industry meeting.
On the meeting or on the work from Constantino, sorry?
Around the work from Constantino's story.
Yeah. So I found very, very interesting. I mean, the part that you only use one receiver for both kind of lines, I mean, you were here, Dylan, reducing the costs because the receiver is one of the most expensive parts of your QKD system, right? And just using one, having the power of only using one receiver and kind of switching between lines, I find it very interesting. And from a network perspective, I mean, reducing costs is always welcome. Yeah, it's a very interesting technology, I would say.
I think, Constantino, you have really good exposure on the end users. Let's continue the conversation, but now, because we're a bit out of time, allow me to close the meeting in YouTube and then come back to you for the final after the meeting here.